Hey everybody, Mr. Covey here, and I hope you just finished up the Desmos activity, and you are on this last page here with me where we're going to kind of summarize how do you tell these characteristics, how do you tell these features of these graphs by looking at the equation, okay, and that's going to be our goal. This is going to be a little bit overwhelming because there's like a ton of different characteristics, but this is really this one thing that we're talking about now is the focus of the entire unit. Identifying characteristics of rational graphs based on the equations. Okay? Some of these are easy, some of them are hard. I think it's easiest to start out with the vertical asymptotes. I'm going to reference the graph of discovery number 3 when I go through this, okay? Notice that this looks a little different than the equation that you had for discovery number 3 because I took the denominator and I factored it. Factoring is going to be super helpful to see these characteristics. So if you look at this graph and you look, do this whole thing here, and you look at the vertical asymptotes, there's a vertical asymptote at -3. Again, it's kind of like a vertical line in the graph. There's a vertical asymptote at 4. If you look at this equation, why are those showing up at -3 and 4? It's because of the x minus 4 and the x plus 3. Okay, so x plus 3 gives you a vertical asymptote of -3. X minus 4 gives you a vertical asymptote of +4. That makes sense for a couple of reasons, but let's write that down first. So to find the vertical asymptotes, you look at the denominator. I'm just going to use a generic rational function, n of x divided by d of x. So you look at d of x, and you're really figuring out when it equals 0. You're like solving an equation to figure out when d of x equals 0. It helps to factor, it makes solving that easy. And the reason that makes sense is because if your denominator is 0, your function is undefined. You can't divide by 0. So if you have a denominator of 0, it kind of makes sense that the graph would be messed up. How does it look messed up? Because it got a vertical asymptote. Okay. How does the domain connect to the vertical asymptotes? Well, basically your domain is everything except for the vertical asymptotes. So basically, for your domain, you just want to exclude the vertical asymptotes. And I'm just writing that in words because the way I want to do that is with interval notation. So if you jump back to example 3, hey, you got a vertical asymptote at -3 and a vertical asymptote at 4. So your domain is, well, you can start out at -infinity. But once you hit -3, you're not allowed to have -3. So I'm going to put a parenthesis. You can pick right back up at -3. But again, I have a parenthesis because it can't be -3. It can be anything except for -3. Okay, you can go from -3. We're good. -2 works, -1 works, 0 works, 1 works, 2 works, 3 works, 4. But then we have to stop there. It doesn't work. Don't want to include 4 in our domain. But I can pick right back up at 4. Go anything bigger than 4 works. Okay, those all should have parentheses there. So from -infinity to -3, from -3 to 4, and from 4 to infinity. Basically, it's everything except -3 and 4. The way to put those together is to put a U for union between them. So it's like that chunk plus that chunk plus that chunk. Okay. Next, zeros. Remember, zeros are x-intercepts. Okay, so how do you find x-intercepts? Well, let's go back to example 3. In example 3, let's look at the graph. The x-intercept was right here at 0.667. Okay, that's 2/3. How did this give us 2/3? Well, if you set the numerator equal to 0 and solve that, it tells you an x value that has a y value of 0. In other words, it tells you an x-intercept. Okay? So how do you find the zeros, the x-intercepts? You set the numerator, and here I'm calling the numerator n of x. You set n of x equal to 0. Okay? So denominator equals 0, vertical asymptotes. Numerator equals 0, tells you x-intercepts. Okay? How do you find the y-intercept? You always find the y-intercept the same way. Since first grade, you're finding y-intercepts. Make x equal to 0, plug it in. You always find y-intercepts. So for this one, plug in 0. What's 3 times 0 minus 2? -2. What's 0 squared minus 0 minus 12? -12. So what's the y-intercept? 1/6. And it'd be nice to write it as a point. So our y-intercept 0, 1/6. Okay, and if you go to our graph, oh look, 1/6. 0.167 is 1/6. Okay. Cool. I hope those aren't too bad. The horizontal asymptotes is where it starts to get tricky. Okay, and this is the really important part. Let's jump back to the first example. And here, the horizontal asymptote was at y = 1. Okay. For the second one, it was at y = 3. And for the third one, it was at y = 0. Okay. Graphically, we're talking about a horizontal asymptote. Remember, we're talking about a horizontal line that the graph approaches. In this case, that, that is the horizontal asymptote. I know what you're thinking. You're like, wait a second, Mr. Cody. You couldn't cross a horizontal asymptote. It's actually not true. It's something that math teachers tell kids because we like to make stuff up. No, because it's kind of confusing. But like, that still counts as a horizontal asymptote even though we cross it. The reason it's a horizontal asymptote is because if you look at this line y = 0, and as you go to the right, we're getting closer and closer and closer to it. And if you look as the graph as it goes to the left, we're getting closer and closer and closer to that blue line. So that blue line counts as a horizontal asymptote. I know it's weird that we crisscross it in the middle. The important part is that you don't cross it on either end. Okay? So then back to how do you actually figure that out? This is hard, so I'm just going to kind of tell you guys. The reason that the third one has a horizontal asymptote of y = 0 is because the degree of the numerator, remember degree is the highest exponent on the x, so the degree of the numerator, which is 1 in this case, is less than the degree of the denominator, which is 2. Okay, so when you're trying to determine a horizontal asymptote, you're really looking at degree of the numerator compared to the degree of the denominator. Those are the things you're comparing. Again, degree is highest exponent. Okay, so if denominator, if degree of denominator is bigger than degree of numerator, as was the case in the third example, then your horizontal asymptote is y = 0. Sometimes people call that bottom heavy. They call it bottom heavy because the bottom is bigger. X squared is way bigger than just 3x. So it's bottom heavy for that reason. Okay. The second possibility is the degree of the numerator is actually more than the degree of the denominator. So the degree of the numerator, say like you have a third degree polynomial and x cubed on top, and you just have an x squared on the bottom. If this is the case, there is no horizontal asymptote. We didn't give you guys one of these. We're going to explore these more in some of the coming videos. Okay, so there's several more videos. So in those ones, you'll see some of that. But in that case, there's no horizontal asymptote. So you got degree of denominator bigger than degree of numerator. Degree of numerator bigger than degree of denominator. Well, what's the third possibility? They're the same. Okay? So the third possibility is degree of the numerator equals the degree of the denominator. Okay? Okay, so if the degree of the numerator equals the degree of the denominator, okay, and we have a third situation here. Oh, I forgot to say something about the second situation. You know how we called this first situation bottom heavy? Because the bottom was bigger than the top. We call it when the degree of the numerator is bigger than the degree of the denominator, we call it top heavy. Okay, so we got top heavy When you have like cubed on top and squared on bottom, that's top heavy. And that's when there is no horizontal asymptote. I always call this third situation even heavy because there's not really a good name. You got bottom heavy, you got top heavy, and you got even heavy. So when the degree of the numerator equals the degree of the denominator, let's look at an example of that. And that's like those first two. So if you looked at like the first equation, the degree of the numerator was 2. It was a square. The degree of the denominator was squared, so the asymptote was 1. Like, oh, it's just 1. Except for in this one, the degree of the numerator was 2. It was squared. The degree of the denominator was 2. It was squared. But our asymptote was at y equals 3. The reason for that, and again, this is kind of hard to see, is that you're really looking at the coefficients, the leading coefficients. So in this case, the leading coefficient was a 3 in the numerator, the leading coefficient in the denominator was a 1, and you divide those. It's the ratio of those. So 3 divided by 1 is 3, and so you have a horizontal asymptote at 3. In the first one, the leading coefficient was 1 for the numerator, the leading coefficient for the denominator was 1. The ratio of those, when you do 1 divided by 1, you get 1, and that's why there's a horizontal asymptote at 1. Okay? I know it's a little complicated. We'll practice this a ton more, don't worry. I'm kind of just summarizing big ideas. So it's y equals the ratio of the leading coefficients. Okay. The last thing is end behavior. Remember that end behavior, it's talking about what happens at the ends of the graph. It always looks like this. It always looks like this. All you have to do is fill in those two things. Like you have to, that's what you're trying to figure out. Remember what you're talking about here is this is saying, as your graph goes to the right, it goes. You're trying to say where it goes as you go to the right. Okay. This part, as x goes to negative infinity, is saying, as your graph goes to the left, it goes to, then you have to answer that question. If you look at a graph, a rational, oops, sorry. So like here's that third one. If you look at the graph and you look at the end behavior, what's happening at the end is really just the same as the horizontal asymptote, because that's what a horizontal asymptote is. It's what your graph is approaching at the end. So all you need to do is look at the horizontal asymptote, and that tells you what's happening at the end. It tells you that the graph's getting close to the horizontal asymptote. That's what is happening at the end. Okay. So when you're trying to identify end behavior, as x goes to infinity and as x goes to negative infinity, y is just going towards the horizontal asymptote. If there is a horizontal asymptote. If there's not, that's another issue. We'll talk about that more in later videos. But if you know the horizontal asymptote, then the end behavior just goes towards the horizontal asymptote. So for instance, in this one here, once you identify that y equals 0 is the horizontal asymptote, well then as you go to the right, y goes to 0, and as you go to the left, y goes to 0. Same within this one, once you identify y equals 3 as the horizontal asymptote, well then the end behavior is as you go to the right, your y values get closer to 3, and as you go to the left, your y values get closer to 3. Okay. Again, we'll recap this all more in the actual videos teaching this stuff, but I hope messing around with Desmos gave you a little bit of an idea about how some of this stuff works. And that concludes this video. Thanks for watching, guys.